Back in the electrostatics chapters, we moved as quickly as possible to using Gauss's theorem instead of Coulomb's law for calculating electric fields. The reason, of course, is that Gauss's theorem allows you to exploit the symmetry of the electric field lines that surround a charged object, and by taking advantage of that symmetry, you can set up an integral that's much easier to solve than the brute force methods. So too, you will see that Ampere's law is similarly useful in the magnetostatics unit for being able to take advantage of symmetry and avoid all of the brute force nastiness of the Biot-Savart law. So I'd like to start by simply making some comparisons between these two laws so that you can see that what you're about to learn is not terribly difficult after all. It's simply an extension of the same kind of ideas into the realm of magnetic fields. With Gauss's theorem, of course, the cause of the electric field was some sort of charge enclosed inside a Gaussian surface. So too, for Ampere's law, we're going to be talking about currents that are enclosed by some sort of loop. The effect of this enclosed charge was an electric field, and the effect of an enclosed current is a magnetic field. The thing we were calculating was the electric flux, and the thing we're calculating now is the magnetic circulation.
Gauss's theorem, you'll recall,
relates the electric flux to the enclosed charge. Ampere's law looks very similar. Both of these reflect something about the nature of the universe in that the electric flux depends upon the vacuum permittivity that the great turtle set forth, whereas the magnetic flux and magnetic field depend on the magnetic permeability, equally important. The units for electric flux were given by a field strength multiplied by an area, as you can see on the left side, or by a charge divided by permittivity. The units for magnetic circulation are analogous. They are a field multiplied by a length, or a permeability multiplied by a current. Do we get to take advantage of symmetry? Of course, in Gauss's theorem, the answer was yes. And in Ampere's law, we'll see the answer is also yes. The type of symmetry I'd invite you to think of as sort of a 3D symmetry for Gauss's theorem, in that we were choosing things such as Gaussian spheres or Gaussian cylinders, things that took advantage of the fact that the electric field is three-dimensional. And so when you're doing this surface integral, you have to take advantage of the fact that you've got field lines poking out in all directions through your surface. In Ampere's law, by contrast, because we've sort of gotten a reduction of dimension with these expressions, here field multiplied by area goes to field multiplied by length, there is a similar sort of reduction in dimension that you'll see for the kind of so-called Amperian loops that we choose that will go into this expression. So there'll be things like circles and rectangles. After all, a circle in 3 dimensions is a sphere, and a cylinder projected down into 2 dimensions, at least in one particular projection, would be a rectangle. In either case, you'll find yourself setting a sort of pattern and procedure for how to do these kind of problems, and always trying to fit your problem within that framework will really help make it permanent for you.